When we introduce the idea of current, we use the analogy of water flowing through a stream or a pipe. We can continue that analogy if we want to now talk about the different paths we could have a current of water or electric charge to flow. So if, again, I were to imagine some sort of body of water going through a river, say, traveling in some direction at velocity v, I can talk about the amount of water going through at any given moment, use that velocity, and I could talk then about that current of water, again, based on its quantity and its speed. Now, if I were to imagine that there were, say, some rocks or stones or something in the way, the amount of water that ultimately needs to go through any part of this river still needs to be the same amount. Well, we can imagine if we were to, say, throw a lot of rocks in the way of this river, we might end up slowing the flow of the water. But if we still have the same sort of slope for the hill, things like that, we would expect that we'd still have to have the same amount of water flowing through. And if we were to go back and forth between rocks in the way, not rocks in the way, the current would still end up being the same. So now let's consider the case with electric current. We'll have a battery, and we'll have our wire going all the way and connecting around. So we'll be going through one single loop. And so we can imagine the flow of the current going along in this direction. Now, if I were to add in a resistor here, say, then I know that there would be some power given off by that resistor. We could measure that just fine. But what would happen to the current, the total amount of current going through this loop? Well, no matter how much current is going into the resistor, it has to be ultimately the same that comes out of it. If I were to add another resistor, that should be the same. And even more importantly, the amount going into the front of this resistor needs to be the same amount of current popping out of this resistor. Because ultimately, where could that current otherwise go? If we're talking about the movement of electrons, say, well, the electrons can't appear and disappear. There's going to just be some finite number, so whatever x goes in, it can't go anywhere else. So that x has to come out even of the second or third or any other number. So we would say that all of these resistors and any more that we might want to add to this setup, no matter what the case, they would all be in series with each other. And the key point then is that the current going through resistor 1, going through resistor 2, we think about all these different currents through all these different resistors. Now, I'm not going to say I know what these resistors are. I'll just give them the nice labels of 1, 2, 3, and 4. But because they are all in series, because current is something that is conserved in a loop like this, I know that every one of those resistors will have the exact same current. Whatever integer I have here for that resistor, it'll be the same amount of current no matter what. Notice though that won't mean the same voltage in each case. Remember that our equation that relates current, voltage, or potential difference, and current and resistance is supposed to be our friend V equals IR. So, if the current is the same in every case, but if R is bigger in some cases, then the voltage difference, the change in potential across each resistor will be different. Which makes sense. If you have the same amount of flow through each resistor, but each resistor might have a different amount of resistance, then there might be a greater potential drop, and then you have the more power popping out of those. But all of this was assuming that there is just this one path for the current to flow. So it could be the case I have a wire and I have it then seem to split in multiple directions. To understand that, maybe we want to think about what happens with a stream that all of a sudden forks. Or you could also imagine it's a rope that forks. Now you might ask the question, okay, you have water flowing through here. can you say how much water is going to flow this way and how much this way? For example, would they necessarily be the same? Well, you've seen small streams and you've seen large streams connected to each other. You've probably been on the highway, and some people take one route and there's a whole lot of cars there, and on the other side route there's almost nobody. There's really no guarantee, there's no reason to think these two currents would be the same. What we could assume that if the current is incoming this way, and then we have water flowing down these other two little tributaries, that the amount coming in has to be the same as the total going out. So we could say that, for example, the amount of current in case 1 here, we can call this 2 and 3, we could say that that has to be equal to the sum of these two other currents. But obviously this equation isn't going to get us very far. There's an infinite number of solutions to this. If I know the current coming in, there's an infinite number of other possibilities of what those currents could be. So we would need to think a little bit more carefully what's going on. Now, you could imagine that part of the reason some current might flow through one river more than another is how much resistance there might be to that flow. If I had a whole bunch of boulders in this stream here and it made flow very difficult, while this one was wide, deep, and clear, you would think more water would go through that case where there's less resistance. So you'd think there'd be some sort of inverse relationship then with the resistance. But we'll need to be even more careful than that if we want to give a nice mathematical statement as to how much current should be going through each of those tributaries. Or in the case of electrical flow, how much would be going down each wire. But let's remember one other key point, though, about the current in these sorts of cases. So, for example, again, in the electrical case, if I have a loop, that's how I then have a circuit. Circuit literally means going like in a circle, which means also that how much flow of current I had popping out, it ultimately has to be the same amount coming back in. Also, though, it means that if I were some sort of electron starting off here, and I go around and I come back to where I started, well, what would you expect then from the energy of that one particle if we have a nice conservative system? Well, if we have a state function, all the energies are conservative, it means when you're back to where you started, you should have the same amount of energy. And similarly, that you also learned about when it comes to the idea of electric potential, that it is supposed to change over distance, but if you're back at the same location, what's your potential change? 0. So whatever sort of loop you create, going all the way around, you have to have had net 0 potential. So the battery will have some sort of potential difference across it, say 12 volts. And there might be then some resistors here that the voltage drops along, etc., etc. But once you've come back, you are again at basically the same voltage amount you were when you started, no matter what, if you've gone around in a loop. If you haven't gone around a loop, you don't have a circuit, and you're not going to have any flow. So what if now I made this system more complicated, and I now had 2 possible paths for the current to flow through? So some current can go down this way, and some current can go along down this way. Well, for no matter which loop I choose, around this loop, we have to have the same sort of ultimate potential change. Around this longer loop, it has to have the same 0 change of potential overall. And similarly then also with this loop, and any other loop we might draw, this will have to have net 0 potential change. So the only way this is going to work is if across each of these segments, of these parts of the loops, we're going to have the same potential drop. So if there was a 12 volt difference across the battery, then we'd have to have the same sort of voltage difference across here. If not, then we wouldn't have a loop going around, in this case, that would sum up to nothing. So if this had a positive 12 difference of voltage, this would have overall a negative 12 voltage drop. And this loop would have to be the same, otherwise we'd have the exact same problem. So what does this mean is that if I were to put, again, some resistors along the way, say one right here and one right here, call that resistor 1, resistor 2, there'll be some current flowing along, current 1, current 2, ones I didn't know initially, but what I do know is that the voltage in each case of these resistors will be the same no matter what. So for no matter which resistor I, whether it's 1, 2, or any others I want to add in, I have to have the same ultimate potential drop across that loop. So in this case then, I can see, starting from the same equation we had before of V equaling IR, that if the voltage is going to be constant, that means if the larger the resistor we have, the smaller must be the current going through, which again makes sense to our water intuition. Make it harder for the river to flow, it's going to have less current through. And of course, if I have two possible loops to go through, well, you would expect more water to go through the easier of the two options. So that also means you could imagine that if I were to add some additional loop here with no resistance there at all, well, if the resistance is effectively zero, then the voltage difference then through that loop across this bit here has to also be zero, which means then there'd be no current, as we might, or, well, actually we can't really say much about the current, but we can definitely say there won't be any potential drop there. But from that same loop rule, it means there's not going to be any potential drops across these resistors, and this is what you're going to call a short circuit. Basically the same sort of thing. If you're going to take the path with the least amount of resistance, and then there's going to be the same potential drop over everything. If you made it so there's no potential drop here, nobody's going to take the harder routes, and so you have basically no current, no voltage drop, and you're not going to get any work done at all with this. So this is why you want to avoid short circuits when you're building any sort of circuit or anything like that.